The university thesis of Jvm Bytecode described the motivation for a new programming language. He discussed the shortcomings of, quote, array-based programming environments, and his desire to create a more performant language with the best qualities of Lisp, Python, Ruby, Perl, and several other languages. The Giulia language is the result of that desire to combine the best qualities of all those languages. It's a high-performance language designed to suit technical users that crave the flexibility to pick their own notation. The language has support for a wide variety of operators, which allows scientists to create domain-specific equations that can be elegantly expressed as code. So when you see those crazy operators like a circle with a plus sign in the middle of it, you can use those in Giulia, and you can define it to do whatever you want it to do. Jvm Bytecode joins the show to discuss his motivations for Giulia and how the language has evolved since he started working on it. Giulia seems like a language that is increasing in importance. It seems like a really cutting-edge thing to cover, and I'm glad we got to cover it on this episode. So I hope you enjoy it. Indeed Prime flips the typical model of job search and makes it easy to apply to multiple jobs and get multiple offers. Indeed Prime simplifies your job search and helps you land that ideal software engineering position from companies like Facebook or Uber or Dropbox. Candidates get immediate exposure to top companies with just one simple application to Indeed Prime. And the companies on Prime's exclusive platform message the candidates with salary and equity up front. Indeed Prime is 100% free for candidates. There are no strings attached. Sign up now and help support Software Engineering Daily by going to Indeed.com/SEDaily. That's Indeed.com/SEDaily if you're looking for a job and want a simpler job search experience. You can also put money in your pocket by referring your friends and colleagues. Refer a software engineer to the platform and get $200 when they get contacted by a company, and $2,000 when they accept a job through Prime. You can learn more about this at Indeed.com/prime/referral. That's Indeed.com/prime/referral for the Indeed referral program. Thanks to Indeed for being a continued sponsor of Software Engineering Daily. If I ever leave the podcasting world and need to find a job once again, Indeed Prime will be my first stop. Jvm Bytecode is the co-creator of the Giulia programming language. Jeff, welcome to Software Engineering Daily.
Hi, also Jeff. Thanks very much for having me on.
Yeah, it's great to be here with you. I guess I shouldn't be saying that. So when I was preparing for this show, I read some of your thesis, which describes the motivation for Giulia. And your thesis discusses the idea of scientific or technical computing. Describe what that means. What is scientific technical computing?
That's a good question. So it's very difficult to define it really precisely. And I think ultimately there isn't really a very well-defined domain of what is that kind of computing versus another kind of computing. I think all computing is just computing. But what it corresponds to is essentially people working in areas of applied science, applied math, who have numerical real-world problems to solve. And tend to work with large data sets, large piles of numbers, and the kind of programs that get written in that world.
What are the characteristics of that type of programming that is different from something like building a web app or making a game?
Sure. So there are a couple of pretty strong constraints on it. So first is that people want a very high level of expressiveness because they really want to think and write in mathematics or in terms of the conventional notations of their discipline rather than just thinking in terms of whatever programming language happens to be around. So they need a very high level of expressiveness, and then also they need very high performance. The goal is to get the peak floating point operations per second out of your processors that you can get. So those two constraints drive a lot of it, and they're actually willing to put aside many other things. So traditionally, a lot of, and unfortunately, a lot of kind of software engineering best practices have been kind of left out because people are often working in a research context where they just need to get some novel result quickly, and then they might just throw it away and go on to the next problem. So kind of long-term maintenance is sort of not the priority. Although increasingly people are getting aware of that as an issue in the research world, and it's improving rapidly. But traditionally, that was sort of the non-motivation of these kinds of languages.
It's interesting that you say that, like up front, like, oh, I'm admitting that oftentimes the way that academic code is written is kind of, I don't want to say sloppy, but like relative to industry code, where you write a piece of code and it's going to be in the code base for a decade. It's a much different domain of programming academia is, because you're kind of like, often it's more in service of a specific experiment.
Yes, so that's been the traditional situation of different priorities, but that is really changing now. And now the work is, how can we get the productive and good part about that, which is getting answers and results quickly, without ending up in that situation where you have difficult to maintain code or not very modular code.
So you have talked about users in the past doing scientific computing in, quote, array-based programming environments. What languages are you referring to when you say array-based programming environments?
There have been a lot of them, actually. So MATLAB is really well known. There was also APL, ZPL, quite a variety of them.
And what are the characteristics of those array-based environments? I mean, arrays are in every programming language. They're pretty fundamental to every programming language.
Right. So these have sometimes these have also been called library languages, and the reason being that the main point of the language is really just to provide a certain set of array library functions, and the rest of the language is not as much of the focus. Whatever language allows providing these array operations is what they want, because the array data structure is so all important in this domain, and so the interesting thing about that. Is that the full set of n-dimensional array operations and data types and so on that people want to use is really very, very rich. It has a really rich variety of behavior with lots of polymorphism, lots of variations, and that behavior is actually difficult to express in most languages, and especially most traditional languages like C have a really hard time expressing those APIs. And so, which is what motivated people to make new languages where they could have these array APIs they wanted. Now, in our view, what you really want is a language that just happens to be powerful enough to define those APIs, and then you get the traditional array programming APIs plus everything else that maybe we've been missing all along.
So, when you were doing scientific computing in academia, what were the shortcomings of the languages that you were using prior to developing Giulia?
Well, let me see.
I mean, this post that you wrote, Why We Created Giulia, begins mentioning languages that you're a fan of: Lisp, Python, Ruby, Perl, Mathematica, R, C, but the implication is that there are certainly some shortcomings of these languages.
Yeah, so there are a lot of little incidental things where, again, because of the focus on these array APIs, that part of the language, these languages, was often really, really good. The design of the array functions was mostly really good, but then there are just all kinds of other details that were just ignored and often really misdesigned, which just creates a kind of death by 1,000 cuts situation where you're constantly annoyed by sharp edges in the language. And one aspect of that is actually performance, where the thinking was that, well, we wanted a very high-level language, and high-level languages are difficult to get to run fast. For a long time, people didn't really know how to do it.
Well, what are the? Oh, sorry. Continue.
But they figured that most of the time could be spent in compute kernels inside these array libraries. So performance of the language itself didn't have to matter so much. So performance was just kind of ignored in the design of the language. And this sort of worked well for quite a while. But then as data sets grew and the world gets more complex, people started hitting limits in this thing.
I see. And the performance of these languages has not caught up, or I guess it's just not. Performance was not considered in the fundamental building blocks of the language, so maybe it's hard to go back in time.
Yeah, that's right. So you can do a lot of work on pretty much any language to speed it up, but if there wasn't at least some thought during the design stage of the language to how it was going to run fast or what it would take to make it run fast, then it's usually very, very difficult to retrofit the highest levels of performance onto the system.
So these languages like Lisp, Python, Ruby, Mathematica, what are the features that you appreciated about these languages? What are the best features of these languages that you wanted to mix together in a new language, Giulia, which we will discuss shortly?
Well, for me, table stakes includes things like garbage collection and higher order functions. You just have to have those kinds of features. So those are good. I also like dynamic typing. And I didn't get to mention this before, but it's notable that in this scientific computing domain, perhaps surprisingly, dynamically typed languages have been very popular. Again, that applies to MATLAB, Lisp, Python, and I think I don't know necessarily exactly why that is, but we think it's probably because when people are trying to model a particular domain of science or other kind of technical work, often it has its own conventions and its own notations and its own notions of how things behave, and those can be sometimes quite surprising to computer scientists, and they don't necessarily line up with something that a static type system might accept. And so people like to have a lot of flexibility to have things behave the way that it's natural to them in these kinds of domains. So dynamic typing has been very popular.
Talking about the motivations of Giulia further, this post also mentions wanting, quote, something that provides the distributed power of Hadoop without the kilobytes of boilerplate Java and XML, end quote. And I think of Hadoop as more of an application than a language. It's certainly turned into an entire ecosystem, but it's interesting that you look at it as a language. Explain how you wanted to bake in ideas of Hadoop to the language.
Well, I think I don't know if we're necessarily looking at Hadoop as a language there. I mean, certainly there are parts of Hadoop, like HDFS, that any language can use. They're totally orthogonal to the language, and we have used them. And certainly there are ideas in it that you can reuse in any language. And so actually, originally we were thinking a lot about distributed computing and how it could maybe be part of the language. But I think we ended up kind of deciding that really just could be left to libraries, that there wasn't a language necessarily needed to do in that domain. And I think it's basically because once you're using multiple machines and a network, you have such latencies involved that you can really just handle it at the library level, and you don't necessarily need a compiler to do anything about it.
You remark that technical users crave the flexibility to pick notation for their problems. What do you mean by that? What are you talking about when you're referring to notation?
Well, just how the program is written, what it actually looks like physically.
And how does that fit into your construction of Giulia?
Right. So we like to at least be able to write syntax in a very mathematical, compact, expression-oriented style to the extent possible. So we have kind of one of our design rules is, you want to be able to write something and then look for any possible extraneous characters or punctuation or anything and just remove all of it and just get it down to, what would be written on a line in a textbook or in a paper. And that also involves allowing a lot of operators. We have many, many mathematical symbols in Unicode now, so allowing use of lots of Unicode characters and lots of Unicode operators in the service of getting that kind of mathematical expression-oriented syntax.
So that's not necessarily a challenge that interpreters have not dealt with before. It's just you've got a richer Unicode set to deal with, so you can have richer operators.
Yes, and I think, it'll be interesting to see what other languages make of the available characters in Unicode, but given our background, we just jumped on them and we just used them very gleefully.
Like, can you name one of those characters?
Oh, there are hundreds of them, actually. So there are hundreds of mathematical operators, things like plus in a circle or times in a circle, and just all kinds of symbols. There are lots of things you'll see in math papers that you don't usually see in programs, but now you can see them in programs.
When I write a line of code that is 3 plus with a circle around it, 5, is the plus with a circle around it, is that already defined to do a specific thing, or is it user-defined?
So that, for most of those, we do not have default definitions. We just parse them, and then if you define a library function with that name, then you can import that library, and then you'll have that operator.
That's pretty cool. It makes me think about... So are most of the people that you encounter that are using Giulia, perhaps in an... Well, I guess this would be in an academic environment. Are most of them like solo programmers? Because I can imagine a solo programmer developing her own really, really dense operator syntax, and anybody else that picks up the code is just like, well, I can never understand this.
Yeah, no, there are definitely stylistic pitfalls there. And it's actually usually it's not solo programmers, but usually it's people from a subfield, and there are a lot of subfields that have established notation that looks weird to everyone outside, but it looks totally normal to anyone inside that subfield.
Ah, well, that sounds actually healthy.
Yeah, so that's what you want to see. But if we people police this just at kind of a social level. If you see people going crazy with operators, we'll say, hey, you don't. That's kind of an abuse. You don't want to do that.
Yeah, I think it would be particularly abusive if somebody wanted to audit your research results and you're like, well, okay, now you got to look through this code.
Yeah, it's really just to enable conventional uses that already exist and maybe invent new ones, but not to just go crazy with syntax.
A high-level goal of Giulia is to integrate code selection and specialization. Explain what that means, and then we will go into some of the features that enable that code selection and specialization.
Yes. So this was one of the core design ideas maybe in the language, which was that looking at these functions that are used in this domain, they have many, many cases. And that exists in two senses. So in one sense, you can have the same function, which will be called with many different kinds of arguments. And basically what you want to do in every case is specialize the function for concrete argument types, and then push type inference through it, and get static types for everything, hopefully. And then you can compile very efficient versions of the same function for different argument types. So the different argument types might be int and float, say. But in full generality, there are, of course, a lot of cases. And then in the other side of it is that people often want to write manual implementations of multi-argument functions for different cases of arguments. And they want to have the system dispatch to the right definition at each call site. And so those two systems really, if you think about it, we realize they're really kind of the same thing, because if you have a compiler that's generating specializations for different argument types, well, when you get to a call site, you want to be able to dispatch to one of those specializations so that you get the fast version of the function. So you need that mechanism in there, and then when you have that, you might as well just use the same thing essentially as your object system and let people add their own definitions and dispatch on those as well. And so it's the same system in Giulia.
Giulia is dynamically typed, and you mentioned this multiple dispatch feature of Giulia where you can have different functions that have the same name. They respond to different types of parameters. Is it a challenge to implement a language that has multiple dispatch and dynamic typing?
Basically, yes. It certainly is. When multiple dispatch was first invented, it was in kind of the Lisp era, and CLOSS, the common Lisp object system, is actually a multi-method, multi-dispatch based object system, and that was certainly dynamically typed. So there's not really a conflict between them. They kind of grew up together, but people have been wary of the challenges of implementing it efficiently. So in C++, for example, you can dispatch on multiple arguments, but only on compile time types to make sure that there won't be any of that kind of dispatch overhead at runtime. But to us, that's really just a premature optimization, and you should really just allow the full dispatch power all the time, and hope that you can make it as fast as possible, and hope that the compiler can remove the overhead as much as possible.
What else is unusual or remarkable about the Giulia type system?
So what we are able to dynamically dispatch over goes beyond what most multi-method systems have been able to do. So usually what's happened is every object has a class, basically, and you'll just a system will just get the class of each argument and then just use those and dispatch on that. But we go farther than that. Since the classes are parametric, they can have a type parameter, like you can have not just array, but array of int, array of float, and we can dispatch on the whole type. So we can have we have some types with this kind of nested structure where there are object kinds of types with parameters, and then there are also tuple types, and so we can dispatch on the entire nest of whatever the structure of the type is. So the dispatch takes into account a lot more information. And so that makes it gives you more power for adding definitions. You can more narrowly specify exactly what your method is applicable to, and it provides more information to the compiler for specializing code on. So that really gives us a lot of power.
We've talked about other types of array-based languages. Let's talk about Giulia arrays. How do Giulia arrays work?
Giulia arrays are not very surprising if you know MATLAB or NumPy or one of those systems. It's just an ordinary multidimensional array type stored in column major order.
Okay, fair enough.
They are not too surprising. But what's happening now, though, is because all of the array functionality is defined in Giulia itself. It's pretty easy to write libraries that define new kinds of arrays and have them perform just as well and behave, in a first-class way as the standard array type. So we're seeing all kinds of these things now, like arrays with different index domains, like different ranges of indexes, distributed arrays, sparse arrays, all kinds of other arrays people are defining.
Giulia uses composition over inheritance. Can you contrast these two and explain why this is important?
So we allow inheritance from abstract types. So it's basically that you can't inherit from anything that's also instantiable. So there's no concrete inheritance, but there is inheritance of abstract types.
How would you define? Many people are familiar with inheritance. I think people are less familiar with composition. How would you explain that term?
So composition is basically when you have two kinds of objects that interact in some way, and instead of having one inherit from the other, you just include a reference to it and just use it as needed.
And as we have discussed, Giulia is known for its high performance. Actually, I looked at the benchmarks. It's approaching the performance of languages like C, which is pretty impressive. Why haven't previous scientific computing languages had this level of performance? Is it just because they didn't? Is it like what you said earlier, that they just were not considering performance, or is there something about it that's really hard to do?
Yeah, so in some cases, the languages have kind of gotten stuck with strange rules in the language that make it difficult to compile, and then they're reluctant to change those or unwind those because there's a big base of code they don't want to break, and so they get kind of wedged. And so we solved that by just cheating and starting over with a different design.
Although for some purposes, Giulia will call out to C functions directly. When is this useful? When would it be of higher performance to just call out to C functions rather than having that function execute in Giulia?
Well, there are lots of really good libraries that already exist, and you want to be able to reuse them. So things like BLAS, which does really fast matrix multiply, libraries like FFTW, which does really fast FFTs. These are really, really well engineered things that already exist. So you want to be able to call them instead of rewriting them.
I guess this is nothing new. This is something that other languages do a lot too, right?
Yeah, of course.
What support does Giulia have for parallelism and distributed computing, that stuff that we discussed with the Hadoop ecosystem?
Yeah, so we have a distributed or a kind of multiprocessing library that's been in the standard library pretty much from the beginning, and that's just designed to make it easy to start up Giulia processes, say, on every node of a cluster, and then it makes it easy to do communication between them using kind of an RPC-like system, really. So that's been there for a long time, and it's really just a library. But the mere fact that we included that in the distribution from the beginning, it sort of sent a signal that this is something we care about and we want to support it well. And so that had some impact. And then more recently, we've been working on adding shared memory multi-threading, which is just going to become more important as the core counts keep climbing, and the memory you can put on one node keeps increasing. You can get single machines with terabytes of RAM now, so it's going to be more and more important to support shared memory threading. So we're working on adding that now, and we just released a kind of experimental version of it.
The Serconis monitoring and analytics platform is a leader in accurate monitoring and custom analytics for any tech at any scale. For 6 years, Serconis has given engineers the tools that they need to understand the behavior of their systems, whether it's leveraging anomaly detection and alerting tools to quickly adapt to unexpected changes, or accessing the flexible analytics solutions to plan your resource allocation. Serconis is the go-to platform that enables you, the engineer, to answer the questions that support your problem-solving goals. If you want to learn about how to better understand the behavior of your systems with a monitoring tool that you can trust, go to serconis.com/sedaily for your free trial. Serconis is built by and for engineers, and they know that inaccurate data from monitoring tools can lead to bad decisions, and that's why their platform stores data using histograms, which enables recall of the entire distribution of data. It's not just compressed or averaged data for your alerting. You get accurate alerting and reporting data that you can trust. This method is not used by most competitors in the monitoring space, many of whom may not even guarantee an accurate measurement for a 99% service level agreement, let alone the service level agreements that your customers require of you, which may be higher than 99%. Again, to check out Serconis, go to serconis.com/sedaily. It would support the show, and you would get a free trial. Serconis offers smarter monitoring for smarter engineers. Check it out at serconis.com/sedaily. Thanks to Serconis for being a new sponsor of Software Engineering Daily. We really appreciate it. I'm getting into some shows about in-memory distributed computing. I've done some shows in the past on it. Is there a really big shift that's going on where it's like the Hadoop ecosystem V1 was basically about you've got everything in HDFS, and it's on disk in HDFS. And then when you do like a MapReduce or something, some big execution across your HDFS cluster, you've got to pull all this stuff off of disk and then put it into memory and then do stuff with it. But my impression is that we're moving towards this time where memory is so cheap, and the tools for operating over distributed memory across a cluster are getting really good. You think that's an accurate depiction of the evolution?
Yeah, I agree. I mean, and there's the thing about distributed computing is you kind of want to avoid it if you possibly can, right? Because coordinating multiple machines is always going to be more difficult than just using one machine. Even though, yeah, as you say, the tools are getting much better. But if you can use one machine, why bother? So we are seeing that, I think.
What kinds of tooling has been built up in the Giulia ecosystem? Are there really good hooks for all the all the tools that we want to use, or is it still in its nascent stages?
So there's a really neat package called Cluster Managers, which basically knows how to interface with lots of cluster scheduling, batch queue kinds of software that's out there, like PBS and Sun Grid Engine and all. Like there's several of them, and it basically knows how to interface with all of these, and it puts essentially a one function interface on top of it, where you just say, add n processors, please, and it knows how to do that over many different batch queues.
So Giulia uses the LLVM, which is the low-level virtual machine. And I've been wanting to do a show on the LLVM because I hear a lot about it, but I actually don't know much about it. I think Swift uses it. But anyway, what is the LLVM? Why is it important? Maybe you could describe the development of the LLVM and how Giulia uses it.
Sure. So LLVM is absolutely great. So it's it's aimed at kind of a classic problem in writing compilers, where we have a whole bunch of source languages and we have a whole bunch of processor architectures, and we like to compile every language to every processor. But obviously, you don't want to write a different compiler for every combination of language and processor, right? So you want some kind of an intermediate representation where you know how to compile every language to the intermediate representation, and you know how to compile that one representation to every processor so that you can get what you want. And so there have been many of these over the years. It's been a perennial topic in compiler research of designing these intermediate representations. There have been several, and LLVM was one that Chris Latner designed, and it turned out, many people feel he just sort of got it right. So it's been the one that has really taken off.
What does a low-level virtual machine enable from a fundamental perspective? Because, we hear about the JVM, we hear about things being built on the JVM. There's a whole JVM ecosystem. Obviously, there's a lot of appeal to using the JVM because there's garbage collection built into it. And so if you build a language on top of the JVM, you get access to all of that ongoing progress that goes on in the JVM ecosystem.
Right. So the JVM, so the JVM bytecode is kind of another one of these compiler intermediate representations that can be used for the same effect. And it's an example where although it's very good, it has the advantages that you describe. But many people feel it gets the level of abstraction slightly wrong, if you will. And many people feel it's actually too high level in that it not only lets you generate code, but it also has kind of an object model that it imposes on you, and it brings in a garbage collector. And some people want to write languages that don't have garbage collectors or that have a very different object model, and in those cases it's harder to work with. So the idea of LLVM was to have a more universal program representation that could just represent absolutely any program from any source language. And so that's the LL part, the low-level part, where it has to get down to a pretty low level of abstraction of just bits and bytes so that it's not imposing anything on you that you might not want.
What kinds of things are people doing with the LLVM? Like, how is that ecosystem evolving? Can you talk about some of the specific languages that people are building and what you have enabled? For example, why would you use the LLVM to build Giulia rather than the JVM?
Well, there's a lot of work going on in the LLVM ecosystem. So there are people like us who are writing compilers that target it. And then there are hardware vendors who are working on support for LLVM to be able to generate code for their chips. So if Intel comes out with a new chip, they have people there that work on adding LLVM support for it. So if you're using LLVM, you'll get that automatically. And then there are people who work on compiler optimizations and program transformations and instrumentations of various kinds, and they can just target the LLVM representation for all of their work, and then we can reuse things like that. So, like, for example, there's this project called Poly, which is a loop optimizer, which knows how to do very advanced optimizations and rearrangement of loops. It operates on LLVM, and since we use LLVM, we can just use it.
Now, programming languages, they all have a certain feel to them, and I want to get into a discussion of Giulia in more pragmatic terms. The Giulia usage. We've been talking about Giulia implementation. What feelings does, this is kind of like a touchy-feely question literally, but what feelings does Giulia evoke when working with it? Because we all have, you work with Java, it has a certain feel to it. You work with Python, it has a certain feel to it. What does Giulia evoke?
Yeah, let me see. I think it's really fun. It's a very lightweight and fun language, and you feel like you're wielding a lot of easy power. And it really comes from this. Once you start thinking in terms of multiple dispatch, and it's also what's known as external dispatch, where the methods are basically outside of the objects. So that there are many cases where you're adding functions and they want to do different things on different combinations of arguments, and you can just write those definitions. Here's what I want to do in this case. Here's what I want to do in that case. And so it just has a very fun feeling because you can write all these definitions in a kind of an uncoupled way, and it helps you kind of partialize your problems and focus on a small part of it at once. Which it's, in a way it's kind of combining an object-oriented dispatch with something that's a little bit more like pattern matching to some extent. And so once you get used to that way of doing things, it's really hard to go back, because then if you try to go back to a class-based OO language, you find that if I want a function to dispatch differently, I have to define a new class, but I don't really want a whole new class. I just want a new case of this one function.
There are numerous examples of people using Giulia for a wide variety of applications, and I watched some YouTube videos, read some stuff. What kinds of projects are using Giulia?
We are seeing more and more. So there are now over 1,000 packages registered, covering a lot of stuff. We're seeing lots of kinds of projects. There's lots of course, research groups still using it. It's getting pretty popular in optimization and logistics research, and I think also probably in practice. We're seeing things like teams of data scientists building and deploying models in it. That's starting to happen more and more. It's fairly popular in finance, and people are doing economic modeling, analyzing securities, that sort of thing.
Yeah, I saw a video from JuliaCon where someone named Erica Mosjakowski from the Federal Reserve Bank of New York was talking about economic modeling with Giulia, and she discussed Giulia being useful for a DSGE model, which is Dynamic Stochastic General Equilibrium. DSGE sounds like the type of model that is useful in a lot of scientific applications, actually. When I was looking at the work that she was doing, I could easily imagine Giulia being useful for something like Black-Scholes, which is like widely used in finance and has a lot of like symbols in it, like the type of
yes.
Unicode symbols we're talking about.
Yeah,
that
that's right.
You would want to define. So I guess Giulia must be a great fit for that kind of domain problem.
Apparently so. So the Federal Reserve Bank of New York wrote a great blog post about how they use Giulia. And so that's it's cool. People should check that out if they're interested.
A quote from your company, which is what is it called? Giulia Computing, I think.
Yeah, Giulia Computing. Mm-hmm.
Okay, it's financial modeling requires bringing together domain experts, quants, and traders. Giulia works well for this because it's a broad spectrum language. What does that mean? Why is Giulia accessible to both quants and traders? Maybe you could describe a little bit the inner workings of how these different teams work together in finance.
It has the kind of high-level mathematical syntax that people in those domains like. So it's very easy to read. We really focus on readability of the language. And then also people who are of a more software engineering bent look at the language and they find that it's pretty decently designed. It doesn't have a lot of sharp edges and weird corner cases and bad behaviors because we've tried hard to take those things into account and take advice from many people who file issues and tell us how we should be doing things.
Are you seeing big companies adopt it in wide use, or is it more in like experimental pockets? Like, are you seeing any Google-sized companies adopt it as like a standard for doing research?
So increasingly we're seeing maybe small groups within an organization will adopt Giulia for a new project, say that they might try it out. Now,
in terms of production, I saw a talk that one of your colleagues gave about using Giulia for airplane collision avoidance.
Yeah, this was a really cool project. They were fairly early adopters of Giulia. So this is basically an FAA-sponsored project to develop an algorithm specification that will eventually run. The algorithm will run on planes in flight for advising pilots for how to avoid collisions. And so their charter is to produce an algorithm spec. And the way they did this before was it was basically written in pseudocode for the specification, and then there was a separate reference implementation, and it was kind of unwieldy, and people weren't really sure if the reference implementation was exactly the same as the spec. So for the next version, they wanted to be able to have a spec that was just directly executable, where the code could be the spec. So that they wouldn't have that issue. There could just be one representation of the thing. And then they could take the specification and then directly simulate it and test it, and they would know that the spec they were shipping actually behaved as advertised. And so they needed a language where they could do that, so it had to be basically read like pseudocode, so it was very clear and readable. And then they had to be able to execute it really fast, and they do really big simulations. They try it out on millions and millions of example scenarios, and they subject it to all kinds of analysis, as you might imagine. So they need a lot of performance to be able to run the scale of testing they want to do. And they discovered Giulia, and they said, boy, this is it. This is one of the few things that could potentially do this. So they've adopted that for writing their spec.
There was a show I did a while ago with Leslie Lamport, who created the Paxos algorithm. Yeah, that was a real treat. But he was talking about, I think, with the language that he's working on now a lot. I think you mentioned it, actually. I think it's APL. Is it APL? No, maybe it's not APL. But what is it? I can't remember. But he uses it for formal. What is it? I think it's formal, some sort of formal presentation of. But it's like an extremely formal way of writing code. I don't know. It sounds like Giulia might be perhaps useful for that. As well, I guess that sounds like what you're describing with the airplane collision avoidance stuff.
Yeah, so they do actually. They do both. They do multiple kinds of verification. There's a lot of simulation, and so actual testing, and then there are also formal verifications that happen. So
formal verification. That's the term I was looking for.
Yeah, so they will actually take a symbolic representation of the program and do formal verification techniques over it. So they do that as well with their Giulia source.
That's like an intense form of proof?
Basically, yes, yeah.
Yeah, and for anybody who has worked with Paxos or in an academic setting, good Lord, there are some intense proofs associated with that algorithm. So what is it like to develop a language in academia?
Well, I was pretty lucky. I had... So my advisor was Alan Edelman, and I should also mention that my other co-inventors who started this with me were Stefan Karpinski and Viral Shah. It was really the four of us and discussions among the four of us what really gave rise to the language. So I was lucky in that Alan, I sort of pitched him on this idea, and he just said, okay, that sounds strange and interesting, and he just sort of let me go at it and do what I wanted. Which is actually a little bit unusual, because normally there would be a lot of pressure to publish a lot of papers, and we worked on this for, I think, easily a year or maybe 2 years without publishing anything, which is very unusual, and that makes me a bad grad student by any standard. But Alan was willing to let us do it, so that's really where the project came from.
There have been some other really interesting languages. Well, one other language that comes to mind that has come out of academia recently is Elm. Have you looked at Elm?
Yes.
What do you think of Elm?
It's very nicely designed. Really very elegant language.
Have you talked to him? Do you have any idea how his experience developing that language in academia compared to yours?
Let me see. Yeah, that's a good question. I think he was probably working on problems that were sort of more immediately publishable. I think he was able to come up with some more focused contributions in the area of functional reactive programming that let him get to some sort of research meat more quickly, whereas we had kind of a more unfocused notion of how can we improve this kind of programming.
Yeah, I don't recall what were the motivations for him, or what were his research findings about FRP. Was it just like, this is a really useful programming construct, or was it this programming construct gives you certain securities, or
Yeah, I have read it. I don't remember it in detail, but I believe it was. I think he basically came up with a better way to do it that made it more practical in some way, either in terms of performance or programmability. It was something about the practicality of it, I think.
Yeah, that's kind of getting off topic, I guess, but it's just interesting because I know his language influenced the React programming framework for JavaScript, which has become all the rage. Interesting seeing academia impact industry. I mean, I guess we also have seen that recently with Spark and the whole Berkeley badass stack. What's your experience with academia contrasting with industry? I mean, now you've got your own company. Have you worked at any large companies? Do you have any perspective for how the research process compares between academia and industry?
So I actually have not worked for really large companies. So I don't really have that experience. I've kind of tried to avoid that.
Yeah. Well, what about so how are you translating that to your own experience with the company, with your Giulia company?
But it's interesting. It's pretty different. I mean it's pretty similar really. It ends up being a balance of development work that you're directly interested in and want to do, and then there are other side things you need to do for customers, or then in academia there are always side things you need to do that are working on papers or classes or something. So it's a mix of both in either case.
Does the work with customers push you forward on the quality of the language from the more holistic theoretical perspective?
It definitely does, yeah. Which is why I've been happy to do it really. Because there's nothing like having demanding real world applications to push things along, and it's gotten us to think more broadly about the kinds of data people have in the real world. Things are not always just grids of numbers.
So let's talk about that a little bit more. What does your company, Giulia Computing, do?
We do a range of things. We do sometimes it's just support for teams using Giulia, where we do priority support. Help them with their code, or sometimes prioritize fixes and improvements to Giulia itself. And then sometimes we do a little bit of custom development. If someone will say they want, say, an interface to a particular legacy system or a certain kind of functionality built, we'll build that. And then we also have some products in the pipeline now. So we have a product Giulia Pro that's basically an easy-to-install, all-in-one bundle that includes an IDE and everything that you can install easily on a variety of platforms.
So, okay, Giulia is free and open source in contrast to proprietary tools like MATLAB and Mathematica, but it sounds like you've got some kind of nice upsell products that are in the works.
Yes, yeah, we're working on that.
Now, do you think that the free and open source nature of Giulia and the fact that it kind of replaces these, well, I don't know if it replaces, maybe it's augmentative or complementary to MATLAB and Mathematica, do you think it will put pressure on those proprietary companies to open up their language a bit more?
Yeah, it's a good question. I mean, especially infrastructure kinds of software and programming languages, perhaps most of all, it's really becoming clear you need to be open source. I think having maybe even if there are cases where proprietary software makes sense, a programming language is certainly not one of them. Since it needs to be kind of for and by developers. You use it to make software, and it itself is software, so you ought to be able to work on it if you're using it. It makes sense. So programming languages really need to be open source, and we've really benefited from that, and I wouldn't want to do it any other way. So for people who have proprietary languages, I'm not sure what's going to happen. It's kind of an open question.
So if there's somebody out there listening right now who is getting ready to start a new software project and they're deciding what language to use, why or why not should they use Giulia?
If you're doing anything numerically intensive that's going to involve data analysis or numerical computing, you should definitely give it a look because we have very good libraries and very good facilities for that. I suppose, the main reason not to use it is usually various kinds of legacy concerns, like you're in an environment that is all Java, for example. If you're say all Java or all C# environment, bringing in Giulia, if you're not getting the benefits from its best qualities, then it might be counterproductive to bring it into that environment.
Put it in a microservice.
But in like a new microservice that takes some data, computes something, and spits back an answer, the Giulia would be perfect for that.
Yeah. Okay. Well, Jeff, what's in the future for Giulia?
Well, we're always working on it, and you can follow along on GitHub, of course. But so our goal now is to come up with a stable 1.0 release, because we've done 5 kind of pre-release versions now. We just released 0.5. And the one thing people are really asking for a lot is to have a 1.0 release where we will commit to supporting it and not breaking compatibility for a long period of time. And where we'll also iron out a lot of the basic issues in the language design and make sure it's really, really solid. So that's kind of our focus right now, is to get to 1.0.
Okay, Jeff. Well, thanks for coming on to Software Engineering Daily. I'm impressed with the Giulia language, and I've been hearing about it a lot from my friend Srini, who has hosted several shows, who is very involved in data science. He works at a place called DataQuest. Actually, yeah, what are you seeing in terms of the data science community adopting Giulia? I guess that's kind of like the more industrial version of the scientific computing that we're talking about in academia, but this we didn't really discuss like kind of mid-sized or smaller-sized companies and how they have data science stacks. How are you seeing that community adopt Giulia?
Yeah, we're seeing more and more of those, of the smaller and mid-size companies are adopting Giulia for data analysis, and so yeah, we're seeing examples of that just trickle in at a steady pace.
Well, that's great. Okay, well, Jeff, thanks for coming on the show. I'll be watching Giulia closely. Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow!